Hello everyone. So in this video, we are going to start our discussions in chapter number 2, the physical layer. Now, in this video in particular, we are going to present an overview for this chapter. Let's go to this textbook. You'll find there are a total of 9 sections in the version we are using. The last section is a summary. So before that, there are 8 sections. So we will find that there are quite a lot of topics, right? So for example, in section 1, we discussed the theoretical basis for data communication, including the signal representation, Fourier analysis. And then based on the frequency domain representation, we will discuss the bandwidth of system, bandwidth of signals, and also discuss the capacity of a channel. So these are the theoretical basis. And then in the next 2 sections, we will discuss the transmission media, including some wired media and wireless media. So in 2 sections. And then in section 5, we have some discussions about digital modulation and multiplexing. So these actually are important issues related to how we could better utilize the channel to transmit or to deliver information, right? So as we can see, this section 1, 2, 3, and 5. So they are basically some physical layer issues that are very important and very fundamental. And besides these 4 sections, we have 4 other sections. Section 4 about communication satellites, section 6 about public switch telephone network, section 7 about mobile telephone system, and section 8 about cable TV systems. So as we can find these are actually communication systems, or you can also call that networking systems. So I could understand that the author used this chapter 2, to discuss this communication system, including satellite, the telephone, the cellular, and the cable TV system, because in the following chapters, so chapter 3 for the data link and so forth, so in the following chapters, the topics are more relevant, more closer to the TCP/IP protocol stack, right? So eventually we want to discuss this IP-based TCP/IP-based applications like the HTTP and then domain name system and so forth, right? So I think that is the main reason why this author put some networking systems in chapter 2, which is about the physical layer. And of course, we can also see that in some of the communication systems, like communication satellite, right? So when we are learning this system, so we have to understand the importance of the physical layer characteristics. Right? For instance, for communication satellite, we should understand that the communication distance is a very important issue, and there is a trade-off between this throughput, delay, and coverage, right? So when we have a satellite that is located in the so-called geostationary geostationary Earth orbit (GEO), so we only need 3 satellites to cover the whole world. But in that case, the throughput is relatively small, and the delay is very large. So that is the feature of the geostationary Earth orbit. And on the other side, you may also notice that in recent years, uh, many people are very interested about this low Earth orbit satellite, right? For example, Elon Musk has a company called SpaceX, and in recent years, they use these rockets to launch a lot of small satellites. They are all low Earth orbit satellites, and it is expected that in the very near future we will have a low Earth orbit satellite system called the Starlink that could provide broadband internet access. So these satellites, they are called low Earth orbit satellites. So you can understand that the transmission distance between the ground station and the satellite will be uh, relatively small, right? So as a result, we will have higher throughput and lower delay. But on the other hand, we will need a large number of satellites to provide global coverage, right? And then in the middle, you can find this medium Earth orbit. So that is in terms of the altitude, uh, it's between this low Earth orbit and the geostationary Earth orbit. So there are other type of satellites like the global navigation system is in particular the GPS or other these navigation systems. So some satellites are in these orbits. So as a result, we will have like a few tens of satellites to provide global coverage, and then so actually this GPS system. So we do not care too much about this high throughput, high data rate, and the major concern is the accuracy of location. And when we have the accurate location, we can also have this accurate timing. Right? So these are the different objectives we could say, right? Compared to this Starlink that aims to provide broadband internet access. So GPS, so the objective is to provide accurate location service. So they are different services, different applications. Anyway, so from these examples, so we can what we can find is that so some of these communication systems they are discussed here in chapter 2. So when we are learning these systems, when we are starting these systems, we have to relate this to the physical layer characteristics and physical layer communication technologies. Okay, so now let's go to the board. Let me explain using the board about the overview for this chapter again. Well, first we need to have the understanding, the layered model. Right? In the last video, I explained that we are going to use a 5-layer reference model. So in this 5-layer reference model, the physical layer is layer 1. Let me just use the PHY. Layer 1, and here we discuss the this layer in chapter 2, right? And then on top of that, we have the data link layer, and there is a sublayer called medium access control. So they will be discussed in chapter 3 for the data link layer and chapter 4 for the medium access control. And then we will have this the network layer. will be discussed in chapter 5. So anyway, we should understand that. So the reason that we partition these functions into different layers is to simplify the design. You want to simplify the design of a very complicated communication network or computer network. Right? And by the way, to the other side, let me just move this a little bit to the right. So layer 2 is the data link layer, and then layer 3 is the network layer. So this is the location, the position of the layer in this 5-layer reference model. Now the next issue, when we are investigating, when we are trying to learn these physical layer topics, we have to understand there are different communication models. So before our further discussions, we have to define these basic terms, right? So in the physical layer, we need to have the device that transmit some signals, and we have some device to receive the signals. So we call them transmitters and receivers correspondingly. And then to physically deliver this signal from the transmitter to the receiver, or the physical medium between them is called a channel. Okay, so we have now, based on this, we have several models. Model 1 is the basic transmitter receiver model. So this model 1, we have 1T, and sometimes we use TX to represent the transmitter. 1 receiver and 1 channel. So this in the middle, this is the channel. And then you can find that we need some signals to deliver the information. Right? So I point the signal to a position closer to the transmitter. So this part, this is the transmitted signal. Right? And then when I'm pointing to this position, so this is the transmitted signal. And here, so this is the received signal. So in our future discussions, we will find that first we will discuss how to represent this signal in the time domain. Perhaps it's the most easy way. And then it is also very important to understand that this signal could be represented in other domains, especially in the frequency domain. Right? And then using this time frequency domain representation, so we can also analyze the behavior of the channel. So this channel can also have a time domain representation, can also have a frequency domain representation. So after we have this basic understanding, so we can derive the received signal based on the transmitted signal and the signal that represent the channel. So which will be discussed in the next video. And then they could also be represented in the time domain and the frequency domain, two major domains. Right? And then based on this understanding, this mathematical tool called Fourier analysis, so we can further analyze, for example, for the channel, so we can analyze the channel bandwidth. Channel bandwidth could be used to estimate the channel capacity, which is the maximum data rate that could be transmitted from the transmitter to the receiver. So these are the fundamental topics to be discussed in the next few videos. And besides these basic models, we also have some other important models. For example, we have 1T to, let me just draw this figure. We have one transmitter, and in the middle there is a channel. We have multiple receivers, R1, R2, and Rn. So this is called a broadcast model or broadcast channel. So this is common in many scenarios. Like, for example, when we are using this Wi-Fi, you should understand that when one device is transmitting the signal, then all the nearby devices, right, within a certain communication range of the transmitter will receive the signal. Right, so this in some cases could help us to provide some useful applications. For example, in the vehicular ad hoc network, the VANET, major application is to broadcast the safety information, safety relevant information. Like, for example, if one car has a sudden brake, so this message could be quickly broadcast to all the surrounding vehicles, right? So as a result, so if we have some other, of course, comprehensive system I mentioned in the last video, so people have developed some prototype for vehicular platooning. So inside a platoon, so we have a sequence of vehicles, and in the test, when we have a sequence of these trucks traveling at a speed like 100 kilometers per hour, that is a pretty high speed, and yet the distance between adjacent vehicle is only 6 meters, right? So you can see that now in such a scenario, so it is very, very important to broadcast this safety information from one vehicle to all the vehicles in the same platoon, right? So corresponding to this channel model, so there are a lot of design issues. Some of them are similar to the simple transmitter receiver model, but we also have some new issues. And another model, let me draw this again here. Model 3 is similar to this broadcast channel. It's called multiple access channel. So in this way, we have one receiver. We have multiple transmitters, T1, T2 to Tn. So in the middle, this is a channel. All right, so in terms of the topology, the shape, right? So these two are the same, but the direction of signals are different. So in the broadcast channel, we have one transmitter. So the signal is coming out from the transmitter, and then it must be received by a lot of receivers. on the other side, so in the multiple access channel, so we have multiple transmitters and a single receiver. So these signals will be transmitted and combined somehow, uh, and then received by the same receiver. Right? So this is a very important scenario, and I would say actually in recent years, many, the state-of-the-art research and development about the broadcast channel and multiple access channel. So later on, when we explain, for example, these cellular systems, the mobile telephone system, uh, we should know that now we are in the era of the fifth generation, 5G, right? But if we look at the physical layer technology, right? So a key issue from 1G to 5G is this multiple access. So this broadcast channel and multiple access channel are very, very important. And then uh, it actually is the key issue in different generations. Like in the first generation, so we consider this first generation, the dominating standard utilized the frequency domain, frequency division multiple access, FDMA. And the second generation is using actually the combination of FDMA and another technology called TDMA, time division multiple access. And the third generation is mainly using the code division multiple access. And 4G is using the orthogonal frequency division multiple access. And then in 5G, so we are continue using this OFDMA, and we also have some newer this multiple access technology like this non-orthogonal multiple access and also space division multiple access and so forth. All right, so that is my observation, right? So we start from the basic model one, which will be further discussed in the following following videos. But we should understand that if you are interested more about the new technology, this broadcast channel, multiple access channel, are more important in recent years. All right, so these communication models are, again, very, very important because before we identify any design issue and the following, possible solutions, we have to understand what kind of system model we are talking about, investigate in each particular model. So there are different associated problems and the relevant solutions. Now let's continue. So here I list a few questions, right, to help you to better understand these physical layer issues. But of course, there are many other issues, but I'm listing only the most basic ones. Now let's start the discussion. So first, how to represent signals and systems. So let's use this basic model one, right? So this signal I already explained, right? Already explained this. This signal will be transmitted by the transmitter, and it is going to propagate through a channel and eventually received by the receiver, right? So to represent this signal, very common, very common representation is the time domain representation. Very simple. If you have a signal, you can measure the amplitude over time. Let me just use this A. Amplitude can be varying over time. So we call that, use a small letter s, t. So this amplitude could be measured, and there are some examples like the voltage or the current. So if you have some knowledge about the electrical circuits, right, so you can measure the voltage between 2 points in the circuit. If you have a link in the circuit, you can also measure the current passing through this link. Right. Of course, there are many other characteristics we could measure, like power or some other features. Right. So the common feature of all these signal in this domain is that we can measure them over time. Right? And then once we put all the measurement in this graph, this amplitude over time, so we get the representation in the time domain. So this is the time domain representation. And then it's very important to understand there are other domains, like in particular the frequency domain. And now in this domain, we have the horizontal axis represent the frequency, and the vertical this axis again represent this. Let me use A prime. It's an amplitude, but it is the value in the frequency domain. And usually you can find something like this, right? Something like this, frequency domain representation. So there is a very important tool that link these two domains is called the Fourier analysis. So using Fourier analysis, we could convert a signal in the time domain to the representation in the frequency domain. So keep in mind that they are the same signal. Let me just put this here. So this is capital letter S, and with variable f. F is the frequency. And in reality, this could be more complicated because in the frequency domain, we may have this complex. So we may have this complex number. So you may have two figures like this, because in the frequency domain, usually we may have this complex number to represent the value. Anyway, so I'm not going to further discuss this because we will have some other following lectures to discuss this time domain representation, frequency domain representation, and the Fourier analysis. Okay, so just now we have tried to explain. So when we have signal, so we have the time domain representation and frequency domain representation. And then for the system, actually this system has a specific meaning, right? This is for the channel. Sometimes people use this because this system is coming from a course. Usually when people are learning these the basics about the systems, there is a course with title Signal and System. Signal and Systems. So in this course, so the term system is used because it is the most general situation. Like for example, if we go to this Wikipedia, you can find that this the most simple system is called a linear time invariant system, a linear time invariant system, LTI system. So a lot of concepts which we are going to explain in the next video are relevant to this system. Right, so it's linear, so it means that when we have a certain input, so the linear combination of these inputs, uh, I mean, this input pass through this LTI system. So in terms of the output, we can still get the same linear combination of the output is still the linear combination of the outputs of individual inputs. Right? And one interesting issue is that when we have this time domain representation like this signal, the system which is also represented by time domain representation, so the output is the convolution of the input and the system in the time domain. But in the frequency domain, so apparently this in the Wikipedia, the transform used is called Laplace transform. It's a similar type of transform, but we are going to use the Fourier analysis. But it's similar. The conclusion is similar. So in the frequency domain, the output will be the input times the system. So anyway, here I'm just trying to explain that. So for the system, in our case, right, the signal and system in this context, so when we are talking about the communication scenario, so the system is the channel. Now let me explain a little bit about this situation. So let me use the basic model. One transmitter, a channel, and a receiver. So to represent this channel, so what happens is that we could just transmit a pulse. We could transmit a pulse. You can find that this pulse in the time domain is just a vertical line. In the time domain. But when the receiver received this signal, so there may be a pattern like this. So this is called the impulse response. The impulse response. So the reason is it's quite straightforward, right? For example, when we are using this wireless transmitter as the example, so when we send a signal, so this signal will be transmitted to some antenna, and I previously explained that this channel could be considered as a broadcast channel, right? But the idea is that this signal will be disseminated to perhaps all the directions, and then some signals will pass. So you can see this wireless transmission scenario. So we could have some pass between the TX and RX, but we may also have some other objects. So as a result, you may have this deflection. Deflected signal. So in wireless communication area, we call that multipass, which is a very common scenario. Right? We will always have this. Right? So in this wireless communication scenario, So as a result, so you can imagine that if we send a single pulse, a pulse is transmitted at a transmitter side. So this pulse, because of this multipass effect, here I'm only drawing these a few objects, but you can imagine in reality, so there could be infinite number of objects to reflect or deflect this signal. So as a result, when we send a pulse at the transmitter side, we will receive uh, impulse response like this, right? And sometimes people call that uh, time domain dispersion. Anyway, so what we have to understand is that for any channel, right, this channel could be represented by a signal in the frequency domain. Right? So we can call this h of t. For example, in the Wikipedia, you can also find this, right? H of t is the impulse response, the time domain representation of the system. So with that, so we can actually combine these two, right? This channel as a system actually can also be represented by the time domain in the transmitter side, the receiver side. So by comparing this transmitter side and receiver side, we can get the impulse response. So later on, we will find that. So in this particular example, I'm using a pulse, but when we understand this Fourier analysis, Fourier transform, so we could understand that this impulse response could be estimated when we send some sinusoid signal with the same frequency. So we can estimate this impulse response uh, in that with respect to that particular frequency. All right, so now this is an important point. So to represent a signal and then to understand that a channel can also be represented by a signal, right? Next in our discussions, you should keep in mind the next problem. So given the signal, how to analyze its bandwidth, right? So previously I have drawn this frequency domain representation for the signal, but as I say, we could have these two figures. Now let me draw these two. So this one for real part and another one for imaginary part, right? But we want to combine these two, right? Combine these two, and eventually we get this so-called power spectrum density. That is, we want to find these to use a formula to combine this real part and imaginary part to a positive number, positive real number. So this is called a power spectrum density. Again, the shape is more or less like this. And when we have the power spectrum density, so we can further define other features like we can specify the peak. You can also specify the reference. So when we have this reference, for example, the reference is, in this case, 1/2 of the peak. Then you can find these two intersection points, F1, F2. So the bandwidth equals to F2 minus F1. Right, so that is the basic method. We estimate the signal bandwidth. As I have explained previously, so you should understand that the channel is also represented by a signal in the time domain. So we can use this same method, drawing this power spectrum density for the channel, and then specify a peak, and then specify the reference so we can get the bandwidth. Right? So that is a relevant issue. And then, so using this understanding of the channel bandwidth, so we have this h of t, that is the channel's time domain representation. We have h of f, and then from h of f, we could have this power spectrum density of this communication channel, right? Communication channel, and then so we get this bandwidth B, and we could use some methods like the Nyquist capacity theorem to estimate a bandwidth. We could also, this is N, right? Use the Shannon capacity theorem. Using the Shannon capacity theorem to estimate the capacity of the channel. For example, we can estimate one channel is, the capacity is 100 megabit per second. So when you have this capacity, according to the definition, the capacity means the maximum data rate that could be accommodated. Right? So we need to think about how to generate some particular signals in order to achieve. Right? So when we have this, so there is a issue how to achieve this capacity in real communication systems. Right? So which will be further discussed. But anyway, so for these three problems, is how to represent a signal, and given a signal, how to find a bandwidth, and given the communication channel's bandwidth, how to find its capacity. This will be discussed in section 1. And following that, once we have some basics, so we are going to discuss these physical media in section 2 and section 3. Section 2 for wired, section 3 for wireless. And also in these two sections, we should understand, or we should try to answer the question, what are the characteristics of the communication channel? So previously I have mentioned this capacity, right? The power spectrum density and then capacity of the channel, but we have many more, right? For example, previously I explained that the satellite communication system. So besides this capacity, you should also at least understand the delay, right? Propagation delay of the channel, right? And then if you further investigate, you will also need to understand the noise of the channel, the interference of the channel. There are many other characteristics, right? And how to generate appropriate signal to transmit with the aim to achieve the capacity. So previously we could use the Shannon capacity or Nyquist capacity theorem to analyze, right, what is the maximum data rate. But in order to achieve that capacity, we have to generate appropriate signal by using modulation by using coding. But in this textbook, actually, they are separated. So we have modulation discussed in chapter 1, section, let me see, this is section 5, digital modulation and multiplexing. And for coding thing, I'm sorry, this is chapter 2. Chapter 3, we will discuss this error detection and error correction. Section 3.2. For error detection and error correction. Anyway, so these are the physical layer issues, as I have just explained, that signal representation, signal bandwidth, channel capacity will be discussed in section 1 in chapter 2. And in section 2 and 3, we discuss wired media and wireless media. Right? So we should understand what are they, and then understand or try to learn the characteristics of these channels. And finally, in section 5 and chapter 3, section 2, we discuss how to generate these appropriate signals to transmit to the system. Right? In general, it's a combination of modulation and coding, but in chapter 2, we focus on modulation. In chapter 3, we introduce some coding techniques. And finally, in this overview, and I have also explained, so we discussed several network systems or communication systems. We discussed satellite network in section 4, telephone network in section 6, cellular network in section 7, cable TV in section 8. And at the end, I would like to also summarize the broadband internet access, using real examples. Like we could use the cable TV system, we could use cellular network. Of course, you need to have at least third generation, like 3G, 4G, and in the future we will have 5G. We will also have the fiber to the home, right? Broadband internet access, and we could also have this satellite communication system, like the Starlink. The aim of the Starlink is to provide broadband internet access to people. I mean, anywhere in the world. So with that, we have finished this overview. Thank you very much.